In 1977, a physicist named Sidney Coleman sat down to think about nothing. Not just empty space, but the true nature of the vacuum itself. He wasn't looking for a doomsday scenario. He was working on quantum field theory. His calculations led him to a paper published in the journal Physical Review D. The paper's title was Fate of the False Vacuum. It was dense with mathematics. It was not meant for the public. But inside those equations was a terrifying idea. As Coleman realized the vacuum of our universe might not be truly stable. It might just be temporarily stable or metastable. He described a scenario where, through a random quantum fluctuation, a tiny bubble of a different kind of vacuum could appear anywhere, at any time. This bubble would contain a true vacuum, a state of lower energy, and it would expand in all directions at the speed of light. Inside this bubble, the fundamental laws of physics would be different. Elementary particles would have different masses, the forces that hold atoms together might not exist. As the wall of this bubble swept over the Earth, it would rewrite reality. We would not see it coming. There would be no flash of light, no distant warning. The end would arrive at the same instant we could ever possibly know about it. One moment, you're here. The next, you and everything you've ever known, from your own thoughts to the most distant galaxies, are gone. Replaced by a new alien physics. Coleman's paper laid the mathematical groundwork for the ultimate sneak attack. An end that comes from the very fabric of reality itself. An end that requires no cause, no villain, no warning. Just a single, unlucky quantum hiccup. Number 17, the universe has already ended. The human brain processes information at a finite speed. The signals from your eyes to your brain take time. The electrochemical pulses that form a thought take time. A complete thought takes about 500 milliseconds. Light travels about 150,000 kilometers in that time. We are always living in the past. The world you perceive is the world as it was a fraction of a second ago. This delay is the foundation of a chilling philosophical and physical problem. It's called the Boltzmann Brain paradox. It stems from the second law of thermodynamics. The universe tends towards a state of maximum disorder or entropy. This is the heat death of the universe, a vast, cold, empty place. But in an infinite or extremely long-lived universe, random fluctuations can happen. Over unimaginable timescales, particles in the void could randomly bump into each other and assemble complex structures. The odds are astronomically low, but in a near infinite amount of time, even the most improbable events become certainties. The theory suggests it is far more likely for a single conscious brain to pop into existence from the random chaos than for an entire, ordered, complex universe like ours to form. A single brain, complete with memories of a life never lived, and perceptions of a universe that doesn't exist, is a much simpler structure than trillions of galaxies. This leads to a strange conclusion. If our universe is to last for an incredibly long time, then the vast majority of conscious observers will be these Boltzmann brains. They will be a single freak fluctuation. They will flicker into existence for a moment, perceive a fake reality, and then dissolve back into the chaos. If that's true, how do you know you are not one of them? You can't. Your memories of growing up, the people you love, the history of the world, all of it, could be a random arrangement of atoms that just popped into being a millisecond ago. The end without warning here is existential. The universe didn't just end. It never really was. Your entire existence is the last thought of a brain that formed from nothing and is about to return to nothing. There is no future, there was no real past, the end is happening right now as your consciousness, a statistical fluke, ceases to be. You are not reading this. A random collection of neurons that thinks it is a person reading this is experiencing its final moment. There is no way to disprove it. The very evidence you might use to argue for a real stable universe, the consistency of physical laws, your memories would be perfectly replicated in the momentary consciousness of a Boltzmann brain. The ultimate end without warning is the realization that it has already happened, and you are just the final echo. Number 16, the Great Rip is not in the future, it is happening now. The expansion of the universe is accelerating. The Hubble constant, which measures this expansion, is about 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. This means a galaxy 3.26 million light years away is receding from us at 73 kilometers per second. And a galaxy twice as far away is receding twice as fast. This acceleration is driven by something called dark energy. We don't know what it is, but it acts like a repulsive force, pushing space-time apart. One theory for the end of the universe is called the Big Rip. This happens if dark energy is a form of phantom energy. Its repulsive force would grow stronger over time. The acceleration would not be constant, it would accelerate. Eventually, the expansion would become so powerful it would overcome the fundamental forces of nature. The timeline for a hypothetical Big Rip is often placed billions of years in the future. First, clusters of galaxies would be torn apart, then galaxies themselves, then solar systems. In the final moments, stars and planets would be ripped apart, then atoms would be broken. Finally, space-time itself would be torn asunder, but this assumes a uniform process. Space-time might not be perfectly smooth. It could have flaws, like a sheet of fabric with a small tear. A 2015 study by physicists at the University of Lisbon explored this. They proposed that tiny microscopic rips in space-time could already be forming. Dark energy could be concentrated at these points, creating localized regions where the Big Rip is already underway. These are not explosions, they are points where the definition of space and time breaks down. If one of these microscopic rips appeared near us, we would have no warning. It wouldn't be like a black hole, which has a gravitational field we can detect. A space-time tear is a fundamental end to physics as we know it. The very fabric of reality would unravel. What would it look like? It's impossible to say. It would be like asking what is north of the North Pole. The concepts of looking or experiencing would cease to have meaning as the space and time they exist in dissolves. Earth, the sun, and our entire solar system would be instantly shredded, not into atoms, but into nothingness, as the rules of existence are deleted at that location. We map the cosmic microwave background, we look for gravitational waves, but we have no way to scan for the structural integrity of space-time itself. A tiny, fatal flaw could open up anywhere, at any time. Number 15, A-phase transition in spacetime. The universe has undergone phase transitions before. In the first moments after the Big Bang, the universe was a hot, dense soup of fundamental particles. As it cooled, the fundamental forces separated from each other. The electroweak force split into the electromagnetic and weak nuclear forces. This was a phase transition, like water freezing into ice. The fundamental nature of reality changed. The rules were rewritten. Some physicists believe space-time itself is not fundamental. It might be an emergent property arising from a deeper, more fundamental level of reality, perhaps made of something like atoms of space-time. These would be incredibly small at the Planck length, which is about 1.6 x 10 raised to the power of 35 meters. At this level, our understanding of physics breaks down. This is the realm of quantum gravity theories like loop quantum gravity. If space-time is made of something, it could potentially undergo a phase transition, just like water. It could boil or freeze. A 2014 paper by physicists at the University of Melbourne proposed just that. A quantum fluctuation could trigger a percolation event. A bubble of a new phase of spacetime could form. This new phase might not support the existence of matter or the fundamental forces as we know them. It would expand outwards like the vacuum decay bubble at the speed of light. The trigger could be a high energy event like the collision of two super heavy cosmic rays. Or it could be completely spontaneous. The energy required might be far beyond what we can create at the Large Hadron Collider, but the universe is a much larger and more violent place. The end would be absolute. The wall of this new space-time phase would sweep across the galaxy. Inside, the very concepts of distance and duration might not exist. The building blocks of reality would be rearranged into a new form that would be utterly alien and uninhabitable. We wouldn't see it coming because the information about its arrival could only travel at the speed of light. the same speed as the event itself. It's not the end of the world, it's the end of space and time. Number 14, the cosmic string snaps. Cosmic strings are not the same as the strings in string theory. They are hypothetical defects in the fabric of spacetime. They are thought to have formed during the phase transitions of the early universe. As the universe cooled and the fundamental forces separated, there might have been cracks left behind, similar to the cracks that form when water freezes into ice. These cracks are one-dimensional objects, incredibly thin but immensely dense and massive. A single inch of cosmic string could weigh more than Mount Everest. They would stretch across vast regions of the universe, perhaps even the entire observable universe. These strings would be under immense tension and would be whipping around at near the speed of light. They would warp space-time around them. A cosmic string passing through you would not be like a physical object hitting you. It would be a line of intense gravitational force, but the real danger lies in their interactions. When two cosmic strings cross, they can form a loop. These loops would oscillate, radiating away their energy in the form of powerful gravitational waves. They would shrink and eventually disappear in a burst of high-energy particles. A 2010 study suggested that if a cosmic string loop were to decay nearby, the energy released would be catastrophic. It would be a focused blast of particles and radiation far more powerful than a supernova. But an even more direct end could come from a direct hit. A kink in a cosmic string, a sharp bend moving along the string at the speed of light, could slice through anything it encounters. If a cosmic string passed through the Earth, it wouldn't necessarily destroy the whole planet, but it would slice through it and anything in its path at a fundamental level. The tidal forces and energy deposition along that one-dimensional line would be immense, creating a cataclysmic event inside the planet. We have no way to detect cosmic strings directly. We search for their gravitational effects, like the way they would bend light from distant galaxies, creating double images. So far we've found none, but that doesn't mean they aren't there. A string or a decaying loop could be heading our way right now. The first sign of its arrival would be the moment it sliced through our solar system, an invisible, unstoppable cosmic scalpel. Number 13, the laws of physics are not a contract. We assume the fundamental constants of nature are, well, constant. The speed of light, c. The gravitational constant, g. The fine structure constant, alpha, which governs the strength of the electromagnetic force. All of our physics, all of chemistry, all of biology depends on these numbers being exactly what they are. If you change the fine structure constant by just a few %, stars can't form. If you change the strength of the strong nuclear force, atoms can't hold together. But what if they are not constant? What if they are just local values of a field that can change over time and space? This is a core idea in some versions of string theory. The constants we measure are the result of the shape and size of extra curled up dimensions of space. If those extra dimensions were to shift or change, the constants in our observable universe would change too. In 1998, a team of astronomers studying light from distant quasars found something strange. The light had passed through gas clouds billions of years ago. By analyzing the absorption lines in the light spectrum, they could measure the value of the fine structure constant in the distant past. Their results suggested that it might have been slightly smaller back then. The findings are still controversial and have not been definitively confirmed. But they open a terrifying door. The constants might not be constant. An end could come from a sudden cascading change in a fundamental constant. Imagine a domain wall, a boundary between two regions of space with different physical laws, sweeping through the universe. This is similar to the vacuum decay idea, but it might not be an all-or-nothing event. It could be a subtle change. The fine structure constant shifts by 1%. Suddenly, the fusion process in the sun's core changes. It might become wildly unstable, exploding, or it might fizzle out. The chemical bonds that hold molecules together could change strength. The DNA in your cells could unravel. Electronics would fail as the behavior of electrons in silicon changes. It would be a complete and total breakdown of every system, from the astronomical to the biological. There would be no warning. The change would propagate at light speed. The universe wouldn't be destroyed, but it would become a place where our kind of existence is impossible. Number 12, a message from beyond the brain. String theory, or more specifically M theory, proposes that our entire four-dimensional universe, 3 space dimensions plus time, exists on a membrane, or brane. This brane floats within a higher dimensional space called the bulk. There could be other branes, other universes floating parallel to ours in this bulk. They could be just a millimeter away from us, but in a direction we can't perceive. Gravity, according to this theory, is unique. Unlike the other forces, it is not confined to our brain. Gravity can leak between branes. This could explain why gravity is so much weaker than the other fundamental forces. Most of its strength is leaking out into the bulk or onto other branes. This model, known as the Randall-Sundrum model, proposed in 1999, opens up some frightening possibilities. If branes can exist, they can interact. 2 branes could collide. The collision of 2 such universe branes would be an unimaginable cataclysm. The energy released would be immense, likely triggering a new Big Bang and wiping out the contents of both universes. We would see the sky light up as the other universe became visible an instant before the collision. But light speed is the ultimate speed limit. By the time we saw it, it would be happening. A less dramatic but equally final end could come from something crossing over from another brane. If gravity can leak between them, maybe other things can too under the right conditions. A high-energy event in a parallel universe could send a shockwave or a particle of some unknown exotic matter through the bulk and into our brain. We would have no way to predict or defend against an attack from another dimension. It could be a particle that catalyzes vacuum decay. It could be a pulse of energy that rewrites physical constants. It would be an event whose cause is literally outside our universe. The first and last thing we would experience is the effect. The ultimate unknown unknown. Number 11, the Grey Goo Plague. This is an end that we could bring upon ourselves, and it could happen with terrifying speed. The idea of gray goo was first proposed by the engineer Eric Drexler in his 1986 book, Engines of Creation. He was exploring the future of nanotechnology. He imagined self-replicating nanobots, microscopic machines that could build copies of themselves using materials from their environment. These could be incredibly useful. They could clean up pollution, fight diseases inside the body, or build complex structures. But he also described a failure mode. What if a self-replicating nanobot was designed to consume any and all organic matter to make copies of itself? And, what if it went out of control? A single microscopic machine reproducing exponentially could consume the entire biosphere of the Earth in a matter of days. The math is relentless. 1 machine becomes 2, 2 become 4, 4 become 8. Within a few hours, there would be trillions. They would spread like a cloud of dust, consuming every plant, animal, and human in their path, converting it all into more nanobots. The end result would be a planet covered in a thick layer of lifeless microscopic machines. A gray goo. This is not a slow environmental collapse. This is a planetary conversion. The process would be silent and swift. It might start in a single lab, a single containment breach. The first sign for most people would be a strange, rapidly advancing dust cloud on the horizon. By the time you realize what it is, it would be too late to run. It would be a mechanical plague disassembling the world at a molecular level. There would be no explosion, just a quiet, relentless conversion of life into machinery. While it is not a universe-ending scenario, for humanity, it is an absolute end that could erupt from a single, invisible point of failure with no warning. Number 10, the Strangelet Contagion. Matter in our universe is made of up and down quarks. These are the particles that make up the protons and neutrons in the atoms of your body. But physicists theorize that there could be a third kind of quark called a strange quark. Under extreme pressure and density, like in the core of a neutron star, up and down quarks could be crushed together and transform into a more stable state, a soup of up, down, and strange quarks. This is called strange matter. A hypothetical chunk of this strange matter is called a strangelet. A strangelet would have a unique and terrifying property. According to a 1984 paper by Edward Witten, strange matter might be the true ground state of matter. This means it's more stable than the normal matter we're made of. If a strangelet were to come into contact with normal matter, it would begin to convert it. The strangelet would act as a template, forcing the protons and neutrons it touches to dissolve into their constituent quarks, and then reassemble as more strange matter. This would be a chain reaction. A single, microscopic strangelet could land on Earth. It would fall to the ground and begin converting the planet from the inside out. The process would be brutally efficient. Each conversion releases energy, accelerating the process. Within a short time, the entire Earth would be converted into a single, planet-sized sphere of hyperdense strange matter. Where would a strangelet come from? They could be created in the collision of two neutron stars. The universe is full of these collisions. A tiny piece of debris from such an event could be hurtling through space right now. We would have no way to, detect it. It could be the size of a virus, but have the mass of an asteroid. It wouldn't burn up in the atmosphere. It would pass straight through. The first sign of its arrival would be the start of the planet's conversion. There would be no flash in the sky, just a silent, unstoppable catalysis that rewrites every atom of our world into something else. Number 9, the genesis of a rogue black hole. We think of black holes as being formed from the collapse of massive stars. These are stellar mass black holes. But there is another possibility, primordial black holes, PBHs. These are black holes that could have formed in the chaotic, ultra-dense conditions of the very early universe, just moments after the Big Bang. They wouldn't have come from stars. They would have formed from the direct collapse of pockets of dense matter. This means they could be of any size. A PBH could have the mass of a galaxy, or it could have the mass of a car. A PBH with the mass of a mountain would be smaller than a proton. They would be incredibly hard to detect. They don't emit light. We can only spot them by their gravitational effects, like the bending of light from a star behind them, an event called microlensing. We have searched for them, but found no definitive evidence. A stellar mass black hole entering our solar system would be a disaster, but we would likely see its effects on the orbits of outer planets years or decades in advance. A primordial black hole would be different. A small one, say with the mass of a large asteroid, would be invisible. It would have a powerful gravitational field, but only in its immediate vicinity. It could pass through the solar system completely undetected. If one were on a collision course with Earth, we would have no warning. An object smaller than an atom, but with immense mass, would strike the planet. It wouldn't swallow the Earth whole. It would pass through it like a bullet. Like the entry and exit would create unimaginable shockwaves and release a tremendous amount of energy from the friction and tidal forces. The path through the planet's core would disrupt the Earth's magnetic field and trigger massive volcanism. The planet would be torn apart from the inside. The first and only warning would be a planet-shattering earthquake and a volcano erupting from every point on the globe at once. Number 8, a glitch in the simulation. The simulation hypothesis is not a formal scientific theory, but a philosophical proposition that has been discussed by thinkers from Nick Bostrom to Elon Musk. The argument is straightforward. If you assume that any civilization advanced enough to create a simulated reality would likely create many of them, and if you assume we will one day reach that level of technology, then it follows that there are far more simulated realities than base realities. Therefore, it is statistically more likely that we are living in one of the simulations than in the one base reality. We look for evidence. We test the fine-grained nature of spacetime. We look for a pixel size or a refresh rate in the laws of physics. So far, we have found nothing to suggest our reality is a computation, but that doesn't mean it isn't. A sufficiently advanced simulation would be indistinguishable from reality to its inhabitants. If we are in a simulation, the end could come without any internal physical cause. It could be as simple as the program being shut down. The civilization running the simulation might have finished their experiment. Their project might have lost funding, they might have run out of hard drive space, or maybe the simulation itself has encountered a fatal error, a blue screen of death for the entire universe. The end would be instantaneous and absolute. There would be no expanding bubble of doom, no approaching object. One moment, the universe exists. The next, it doesn't. All of existence would simply be deleted. It is the ultimate pull of the plug. We would not experience it. Consciousness, time, space, and all the matter within it would cease to be in the same instant. There is no warning for a computer being turned off. Number 7, the sky catches fire. A gamma ray burst, or GRB, is the most powerful type of explosion known in the universe. They were first detected by military satellites in the 1960s. For a few seconds, a GRB can outshine entire galaxies. A long-duration GRB lasting more than 2 seconds is thought to be caused by the collapse of a very massive star, a hypernova. As the star's core collapses into a black hole, it fires out jets of plasma from its poles at nearly the speed of light. If one of these jets is pointed directly at Earth, we are in serious trouble. The light and gamma rays all travel at the speed of light. This means we get no advance warning. The first sign of a GRB is the burst of radiation itself arriving. If a GRB were to occur in our own galaxy within a few thousand light years, and it was aimed at us, the consequences would be devastating. The side of the Earth facing the burst would be hit with an intense wave of gamma radiation. It would be like getting a CT scan of your entire body, but hundreds of times more powerful in an instant. But the immediate radiation is not the main threat. Like, the real danger is to the atmosphere. The gamma rays would slam into the nitrogen and oxygen molecules in the upper atmosphere. This would break them apart, and they would reform into nitrogen oxides. This would create a thick, reddish, brown smog that would block out sunlight. More importantly, these nitrogen oxides would rapidly destroy the ozone layer. Within minutes, most of the Earth's protective shield against solar ultraviolet radiation would be gone. The side of the Earth that was facing away from the burst would be safe from the initial flash. But then, the planet would turn. The unprotected surface would be bathed in deadly UV radiation from our own sun. It would sterilize the surface of the land and the upper layers of the oceans, killing plankton, plants, and most animal life. It would trigger a mass extinction event. We are constantly monitoring the sky for GRBs, but they happen in distant galaxies. The scary part is the progenitor stars, the massive Wolf Riot stars that can create them. A star like Eta Carinae, about 7,500 light years away, is a candidate. We don't know the orientation of its poles. It could be aimed right at us, and we would have no way of knowing until the light from its final collapse reaches us. Number 6, a collision with nothing. The universe is filled with dark matter. It makes up about 27% of the mass energy of the universe. We know it's there because of its gravitational effects. It's what holds galaxies and galaxy clusters together. Without it, they would fly apart. But we have no idea what it is. We have never directly detected a dark matter particle. It does not interact with light or with normal matter except through gravity, but does not interact might be an oversimplification. It might just interact very, very weakly. Theories of dark matter abound. One class of theories suggests dark matter exists in a dark sector with its own particles and its own forces, a kind of shadow universe occupying the same space as ours. What if there's not just one type of dark matter particle, but a whole periodic table of dark elements with dark chemistry and dark physics? This opens the door to a strange kind of disaster. Just as our universe has stable and unstable configurations, the dark sector could too. A 2017 paper explored the idea of dark matter bombs. A supermassive black hole could accumulate a cloud of a certain type of dark matter particle around it. This cloud could reach a critical density and then undergo a catastrophic collapse or annihilation, releasing a huge amount of energy. This energy might not be in the form of light or normal particles, but as a blast of dark radiation or other dark sector particles. Such a blast would be invisible to us. It would pass through normal matter with almost no interaction. Almost. If the interaction is not zero, then a sufficiently dense wave of this energy could have an effect. It could deposit a tiny amount of energy into every single atom it passes through. If the wave is powerful enough, that tiny amount of energy, multiplied by the trillions of atoms in your body or in the Earth's core, could be enough to heat things to catastrophic temperatures. The end would come as an invisible, silent wave of something washes over the planet, causing everything to spontaneously heat up and vaporize. We can't build a detector for a threat we can't even imagine. Number 5, the Big Rip's silent cousin. The Big Rip is a spectacular end where the universe is torn apart. It is caused by phantom dark energy, where the density of dark energy increases as the universe expands. But there's a different, more subtle possibility related to dark energy. What if dark energy is not constant but is slowly decaying? This leads to a scenario called the Big Freeze, or heat death, where the universe gets colder and darker over trillions of years. But there is a third option. A team of physicists in 2022 proposed a new model for dark energy. They suggested it could be coupled to the rest of the universe in a way that allows it to suddenly decay. This would be a phase transition. The dark energy that is currently driving the accelerated expansion of the universe would suddenly vanish. The consequences would be immediate and cosmic. The repulsive force pushing galaxies apart would disappear. Gravity would become the sole dominant force on large scales again. The universe's expansion would not just stop accelerating, it would abruptly stop and reverse. The universe would begin to contract. This would lead to a big crunch. This is not an end with no warning in the traditional sense. A big crunch would take billions of years. But the transition itself, the moment the dark energy disappears, would be instantaneous and without warning. It would be a fundamental change in the cosmic rulebook. One moment the universe is accelerating its expansion. The next, it is beginning to collapse. We would have no way to predict this phase transition. Our measurements of dark energy today would not reveal the instability. An astronomer looking at distant galaxies would suddenly see their redshift stop increasing and begin to blue shift as they started moving towards us. The fate of the universe would be sealed in an instant, changing from an eternity of cold expansion to a fiery, compressed end. Number 4, an asteroid we can't see. This seems like a classic, well-understood threat. We are constantly scanning the skies for near-Earth objects, NEOs. We have cataloged thousands of them. We believe we have found over 90% of the ones larger than 1 kilometer, the planet killers. But our methods have a built-in bias. We can only see the asteroids that reflect sunlight. What if an asteroid was incredibly dark? Not just black like asphalt, but vantablack dark. An object that absorbs 99.9% of the light that hits it. Such an object would be almost impossible to see with optical telescopes. It would be a dark shape against the black of space. We might only spot it when it occulted a star passed in front of it, and that would be a matter of pure luck. Worse, what if it came from the direction of the sun? Our telescopes, both on the ground and in space, generally can't look in that direction because the sun's glare would blind them. Or an asteroid on an orbit that takes it around the sun and then straight towards Earth would be hidden in that glare until the last days or even hours. The Chelyabinsk meteor in 2013 came from the direction of the sun. It was only about 20 meters across, but it exploded with the force of 30 Hiroshima bombs. We had no warning. Now scale that up to a 500-meter asteroid. An object like that made of iron and rock would not explode in the atmosphere. It would hit the ground. The impact would release energy equivalent to tens of thousands of megatons of TNT. It would create a crater miles wide, trigger global earthquakes and tsunamis, and throw enough dust and debris into the atmosphere to block out the sun for years, causing an impact winter and the collapse of agriculture. By the time our systems could pick it up from the sun's glare, it would be, too late to do anything. It would just be a new, fast-moving point of light in the sky for a few hours before the end. Number 3. The false vacuum collapse. This is the original sin of cosmology, the idea that started with Sidney Coleman's 1977 paper. It deserves its own deeper look. The idea is rooted in the Higgs field. The Higgs field permeates all of space. Particles get their mass by interacting with this field. The value or energy level of the Higgs field is crucial. We live in a universe where the Higgs field has a certain non-zero value. This is a state of low energy, but it might not be the state of the lowest possible energy. Think of it like a valley high in the mountains. We are living at the bottom of this high valley. It's stable, but there is a much deeper, larger valley just over a ridge. Our current state is the false vacuum. The deeper valley is the true vacuum. To get there, we would have to get over the energy barrier, the ridge between the valleys. Classically, that's impossible without a huge input of energy, but in quantum mechanics, there is a way quantum tunneling. A particle can spontaneously tunnel through an energy barrier it doesn't have the energy to overcome. The entire Higgs field could do this. At any point in space, at any time, a tiny region of the field could randomly tunnel through the barrier to the true vacuum state. This would create a bubble. Inside this bubble, the Higgs field has a different value. This would change the mass of all fundamental particles. The W and Z bosons, which carry the weak nuclear force, might become massless or super heavy. The electron's mass could change, which would alter the size and stability of atoms. Chemistry would cease to exist. Nuclear physics would break. The structures of matter as we know them, stars, planets, people, would be impossible. They would collapse into a crush of exotic particles. This bubble of true vacuum would expand at the speed of light. Its wall would be a shell of pure energy. As it passes over you, reality is rewritten. The standard model of particle physics, our best description of reality, has a disturbing feature. Based on the measured masses of the Higgs boson, around 125 GeV, and the top quark around 173 GeV, our universe appears to be right on the edge of stability. We might not be in a truly stable state, we might be in a metastable one. The lifetime of this false vacuum could be trillions of years. Or it could be a few seconds. The math doesn't give us a definitive answer. There is no precursor. There is no way to predict the random quantum event that starts it all. It is the ultimate cosmological landmine, and we have been tap dancing on it for 13.8 billion years. Number 2. A supernova next door. A supernova is the explosion of a star. A type II supernova is the end of a massive star's life. But a type Ia supernova is different. It happens in a binary star system where one of the stars is a white dwarf, the dense remnant of a star like our sun. The white dwarf's powerful gravity pulls material, usually hydrogen and helium, from its companion star. This material builds up on the white dwarf surface. A white dwarf is supported against collapse by something called electron degeneracy pressure. But there is a limit. This limit is called the Chandrasekhar limit, about 1.44 times the mass of our sun. When the white dwarf accretes enough matter from its companion to cross this limit, it can no longer support itself. It begins to collapse. This triggers a runaway thermonuclear reaction. The entire star is consumed in a fraction of a second. It doesn't just blow off its outer layers, the entire white dwarf detonates in a massive explosion. Because they all explode at roughly the same mass, Type Ia supernovae are incredibly consistent in their brightness. This is why they are used as standard candles to measure cosmic distances, but this also makes them incredibly dangerous. A Type Ia supernova releases a huge amount of high-energy radiation, particularly gamma rays and X-rays. If one were to occur within about 30 light years of Earth, it would be an extinction-level event. The radiation would strip away our ozone layer just like a GRB. The visible light would be intense. For weeks, the supernova would be brighter than the full moon, possibly even bright enough to be seen during the day. It would disrupt the cycles of nocturnal animals, but the high-energy radiation is the killer. The constant bombardment of X-rays and cosmic rays would increase mutation rates and cancer. The loss of the ozone layer would flood the planet with UV radiation. We don't know of any white dwarf systems that are this close and on the verge of going supernova. But finding them is hard. A white dwarf is small and dim. Its companion star might also be dim. A potential progenitor system could be lurking undiscovered in our stellar neighborhood. The process of accretion can be unstable. The final few years or decades before the explosion might not have any obvious signs we could detect from light years away. The first we would know of it is when a new star appears in the sky. By then, the wave of deadly radiation would already be washing over us. Number 1, the light speed wall. This is the simplest and perhaps the most undeniable end without warning. It encompasses many of the other scenarios. The speed of light, about 299,792 kilometers per second, is not just a speed. It is the speed of causality. It is the fastest that any information can travel through the universe. Nothing can warn you of an event that is itself traveling at the speed of information. The bubble of false vacuum decay, the space-time phase transition, the brane collision. The shockwave from a cosmic string, a gamma-ray burst jet, all of these things travel at or near the speed of light. Let's take the GRB. If a star 1,000 light-years away goes hypernova and points its jet at us, the light and gamma rays from that explosion travel for 1,000 years to reach us. During that entire time, there is no way for us to know it has happened. The star itself, as we see it in our sky, looks perfectly normal. We are seeing 1,000-year-old light. The light from its explosion is traveling right behind that old, peaceful light. The moment we see the flash, the moment our instruments detect the gamma rays, is the exact same moment the effects begin. There is no time to prepare, no time to take cover, no time to even comprehend. The warning and the event are the same thing. This is the fundamental limit of our perception. We live inside a light cone of cause and effect. We can only be affected by things in our past light cone, and we can only affect things in our future light cone. An event traveling at light speed moves along the edge of that cone. This means that right now, a wave of cosmic death could be just 1 light second away from us. About the distance to the moon, a wall of energy that will rewrite physics, or a blast of radiation that will sterilize the planet. It could have been created thousands of years ago on the other side of the galaxy. It could have been created 13 billion years ago in the early universe. Its journey has been silent and invisible. And in less than the time it takes you to blink, it will arrive. There is no defense against it. There is no warning. It is the ultimate limitation of living in a universe with a speed limit. The end can be 1 light year, 1 light hour, or 1 light minute away, and the universe will look completely peaceful right up until the moment it isn't.